Okay, so let's do a bit of a case study. It's a case study that I would not be surprised if you're familiar with, but it's a nice one for illustrating some of these points. Okay, and it's the analysis of the nth harmonic number. Okay, so this nth harmonic number is, a kind of complicated expression that comes up all the time in TCS, for example, in the coupon collector problem and elsewhere. So the definition of this is Hn. I guess it's usual to write it with a subscript rather than as a function. And it's the sum of the reciprocals of the first n numbers. Okay, so you may encounter this, and what you really want to know is, okay, well, what is this really, growing like as a function of n? And you may well know already that this thing is very close to asymptotically the natural log of n, log base e of n. But we'll get there. In fact, we're not even going to start by trying to get like such a precise bound. We're just going to try to understand what this is big theta of. In other words, that it's big theta of log n. And especially when you see like an expression like this that comes from a sum, you should always try to do the most unsophisticated things you can first. Okay, so try to go for the most simple way to upper bound things, or the simple way to lower bound things. Usually by trying to make some of the terms look similar so that you can put them together. Okay, so I'll show you a way you can get a reasonable bound on h of n. So one thing you could try to do is get an upper bound. And to get an upper bound, you can say like, well, I'll upper bound it term by term. This 1 I'm going to leave here. Half I'm going to leave here. And I'll say 1/3 is at most 1/2. That's undeniable. And then the 1/4 I'll leave here. Okay, the next thing is 1/5. And I'll say that's at most 1/4. And 1/6 is at most 1/4. And 1/7 is at most 1/4. 1/8 I'll leave it. Okay, I'm going to keep going, but you see, computer scientists really love powers of 2, so this is why we're doing this. Okay, so this is 1/8. The next one is 1/9. That's at most 1/8, and so forth. Okay, and in general, you can group these things into, you can take each number and bring it up to the next highest power of 1/2. Okay, and why is that convenient? Well, this adds up to 1. This adds up to 1. You have 4 copies of 1/4. This adds up to 1. This next thing is going to add up to 1. Okay, etc. And how many groups are we going to have? Log base 2 of n. Actually, there's like some, you have to fiddle for a bit because there's an annoying edge case, like what if it goes all the way exactly to a power of 2, or what if it goes not exactly to a power of 2? I'm not going to go over that fiddling, but you can try to confirm or deny that the following is correct, that it's at most log 2 n floor plus 1. But don't worry too much about these things. It's basically at most log base 2 of n. Okay. And okay, I guess this sort of, if you know this, it proves that e is bigger than 2. But it already gave us an upper bound that's of the right form up to a constant, log n. Okay, so that's an upper bound. Of course, we always, okay, if we only want an upper bound, we're done. It's big O of log n. It'd be nice to also have a lower bound. Can somebody suggest the similar way to try to get a lower bound? Yeah?
Instead of writing 1/3 less than half,
Right, exactly. So kind of bring everything down to the next lower power of 1/2. So this is like a little bit slightly more complicated, but basically the same thing. So it's suggested we'll actually just leave 1 and 1/2 there, and we'll say 1/3 is at least 1/4. Okay, and 1/4 is also at least 1/4. And then 1/5 is at least 1/8. 1/6 is at least 1/8. 1/7 is at least 1/8. 1/8 is at least 1/8. 1/9 is at least 1/16, and so forth. Okay, so hopefully that's also believable. So this is 1. This is 1/2. 1/4 and 1/4 is 1/2. Okay, you have 4 copies of 1/8, so that's 1/2. You're going to have 8 copies of 1/16, so that's 1/2, etc. Okay, so again, you basically have log base 2 of n groups, and each group is contributing at least a half. So this is going to give us a lower bound that's like a half times log base 2 of n. Okay, and if you really handle the fiddly bits, I believe it's at least, I have to check my notes, half times the ceiling of log base 2 n plus 1. Probably this plus 1 is for this plus 1. But again, like ignoring the pluses and the floors and ceilings for these purposes, this is great. We've got an upper bound that's like big order of log n. Okay, so we got h of n is at most order n, and h of n is at least omega of n. Okay, and therefore h of n is theta of log, whoa, these are low log n's. Theta of log n. Okay, and that's in quote unquote standard form. So that's very satisfactory. And 98% of the time in TCS, this is going to be good enough for you. I mean, you don't usually need to know it to this close of precision. We already got up to a factor of 2, which is quite nice. Okay, any question? All right, but while we're here, I mean, sometimes you really do want to tough it out and get the exact constant. So let me introduce one last piece of notation, which I guess I saved, analogous to this big O and big theta and so forth and so on. It's like the analog of big theta, but when you have the constant exactly right. But you might have lower order terms wrong. So one writes that f of x is asymptotic to g of x. This is like a big tilde. It's / sim in tech. This is, let's say, as x goes to infinity. This means that f of x over g of x tends to 1. Okay, which indeed expresses that they're the same, even up to a constant factor, just lower terms are wrong. So equivalently, f of x equals g of x times 1 plus, I like to write this. This is my own kind of quirk, plus or minus little o of 1. Because I don't want to insist necessarily that little o of 1 can be positive or negative. Anyway, if you put this in, it doesn't look wrong. It can only help. OK. And as an example, as the example I just erased, but we know that the sum of I as I goes from 1 to n, which was a half n squared, well, we wrote it like this, plus order 1 over n. OK, this is little o of 1. It means it's something that's tending to 0 as n's getting bigger. So we can say that this is asymptotic to a half n squared. OK, and this is like sort of like the one step better of saying, this expression is theta of n squared. It's telling you even what the leading constant factor is. OK, so if you're really tough, your goal is to maybe find a g of n in standard form, such that your function f of n is asymptotic to g of n. So in fact, let's actually do this for the harmonic number h sub n. And we'll see why it's asymptotic to the natural log of n. And to do this, we have to use a kind of trick or technique. We write it like this. Proposition h of n is asymptotic to natural ln of n. We have to use a trick or technique, which is like the integral trick or integral technique. In some sense, I hesitate to bring it up because it's like a very mathy, calculus-y trick, and I honestly almost never have used it in practice. Yet, both now and in the next lecture when we talk about Stirling, we're going to use it. So OK, I'll tell it to you, and it's kind of cool. Just a warning, though. I mean, if you don't love calculus as much as I do, it doesn't come up that much. It really comes up mainly if you're trying to really nail down these factors. So this calculus trick is to try to approximate a discrete sum by an integral, like in calculus class. So the function in our sum is function 1 over t. Let me try to draw it. OK, so this is the t-axis. This is the function 1 over t. This is 1. This is 1. Let's put 2 in. 2, 3, 4, n. And this is going to be a half. And this is a third, and so forth. OK, and an idea is that this sum, the harmonic number sum, is exactly equal to the area of a bunch of rectangles that I'm about to shade. I'll try to shade it, well, this rectangle. OK, so this rectangle has, all the rectangles I'm going to shade here have a width of 1. And their heights are 1 and a half and a third and a quarter, all the way out to 1 over n. Because I stopped the rectangle right when it's on the curve. OK? And therefore, the total shaded region here, the area of all these rectangles, is exactly h of n. OK, so this is proof. H of n equals the area of the shaded rectangles. And now let's see. Let's start by trying to get an upper bound. And the idea for the upper bound is, well, let's take this first rectangle, which has area 1, and just put it aside. So we got 1. And then you see all the other rectangles are lying below the curve. So if we took the area of the curve from area below the curve from 1 to n, that would be an upper bound on the area of all the other rectangles. OK, so this is the area under the curve from 1 to n. OK, and now we use calculus. So this is 1 plus the integral from 1 to n of 1 over t dt. OK, and then this is 1 plus the antiderivative of 1 over t is ln t. We're evaluating it from n to 1. Actually, in some sense, in some calculus textbooks, this is literally the definition of natural logarithm. So arguably, this is circular. But anyway, we all know what the natural logarithm is, so we can leave it like this. OK, and this is 1 plus ln n minus ln 1. Ln 1 is 0, so this is ln n plus 1. OK, so if we secretly know that this is our target upper bound, then we're in great shape. This is asymptotic to ln n in the sense that the ratio of this and this tends to 1 as n goes to infinity. OK. All right, so now let's try to do a lower bound. And we're going to try to do the same trick, but we need to get some rectangles that count up the sum, which are above the curve. OK, so let me try to do this on the same picture. Actually, let's just take every rectangle here and shift it over to the right by 1. OK, so that'll still be the same harmonic sum. We'll just position it differently. So when I shift this rectangle over, it becomes this one. And when I shift this rectangle over, it becomes this one. And when I shift, now it's getting horrible, but when I shift this one over, it becomes this one. OK, and when I shift this one over, it becomes this one. That goes out to n plus 1. OK, and so you see the area of the rectangles is still the harmonic number. And now it's the amount of area enclosed is above the curve, at least if you go out to n plus 1. So hopefully you can decipher that picture. But what it's implying is h of n is at most, well, the area under the curve from t equals 1 out to n plus 1. Okay, and this is again the integral 1 n plus 1, 1 over t dt, just ln t, evaluated from 1 to n plus 1, which is ln of n plus 1. Okay, so finally we've concluded that ln n plus 1 is less than or equal to hn is less than or equal to ln n plus 1, which is a different thing. I just read it the same way for fun. Yep.
Might have the signs wrong.
The sign's wrong? Oh, yeah. Thank you. Great.
And in the first line, so the first line should be greater.
Thank you. Great. So indeed, actually, this one, ln of n plus 1, is also asymptotic to ln t, which was kind of our goal. Sorry, ln n, which is kind of our goal. So in fact, this establishes the proposition. But let's actually dig in a little bit just to like double check for ourselves why exactly this and this are both asymptotic to ln n. And one reason to do this, just out of curiosity, is to try to figure out which one is closer to being ln n. Or we can compare the error rates between these two things in ln n. Actually, before I do that, let me just say what happens if you want to do this argument even more carefully. You can start to worry about the error of those sort of triangular-y error regions. We're not going to worry about those today, but actually we're going to do such a thing when we do Stirling's formula next time. But just for your own edification, you can see that. So here we've got it's basically ln n up to like some additive constant. It's actually known that h of n is indeed ln n plus some constant, which is called gamma, minus order 1 over n. And gamma is just the constant that makes this true. It's called the Euler-Mascheroni constant. It's like 0.577 or something. And you will probably never need it, but that's good to know about. It's actually a more mysterious constant than e or pi. Like, I think it's not known if it's rational or irrational, albeit it's presumably irrational. OK, so let's actually, in fact, try to compare these two quantities to exactly ln n. So, and this is an example of trying to get things looking like, some function is asymptotic to another function in standard form. OK, so for the first one, ln n plus 1, it's a little bit easier because we can just factor out the desired expression. This is ln n times 1 plus 1 over ln n. OK, and that exactly looks like, well, it no longer looks like what we had written here, which was f of x equals g of x times 1 plus little o of 1. But indeed it is, because this is an expression which this whole thing goes to 1 as n goes to infinity. OK? This other one is like a little bit trickier. And well, this is the kind of stuff that you will need to get used to as you're playing around with asymptotics. So what can we do with ln of n plus 1 to make it look something like this? Well, you have to think a little bit or like play around. But you can use a nice property of ln to do the following. This is ln of n times, you're trying to isolate the main term. You're trying to make this ln n term pop out. So we'll write this as n times 1 plus 1 over n. That's true. OK, and then log of a times b is log a plus log b. So this is ln n plus ln of 1 plus 1 over n. OK? So, 1 plus 1 over n is basically 1, and log of 1 is 0. So this should be basically 0, which is great. But again, we might want to know how basically 0 is it. And to understand this, we do need a bit more calculus. So this is an opportunity to introduce, one more, or remind you of one more calculus tool that you need to do some more advanced asymptotics, which is Taylor's theorem. So let's see. We have Taylor series for log. You can look this up in a book or type it into Maple or Mathematica. or derive it yourself using your calculus, your vast calculus knowledge. Ln of 1 of x, when you think of x as a small number, so when you're in the neighborhood of 1, there's a series for it. It's x minus x squared over 2 plus x cubed over 3 minus x fourth over 4, etc. And this holds for all x between -1 and 0. And exactly, but in general, this is asymptotic to x as x goes to 0. OK, so this is in general if x is small. This is a really small number, near 0. It could be positive or negative. And it's basically proportional to x. You see now x squared is the term you can neglect in this big O notation. OK? And therefore, this thing that we're worried about or questioning about, it's of the form 1 over n plus an error term which is, well, I can't even write, I'll just write big O, 1 over n squared. OK? And now we still actually want to get it to look like this, I suppose. So let me just write it here. We can finally factor out the log n and get that this is ln n times 1 plus 1 over n ln n plus or minus order basically 1 over n squared, but there's even another log n here. OK, so this shows that, again, this quantity is like log n times something that's going to 1. And this is actually telling you how fast it's going to 1. It's going something like 1 over n, even a little bit faster. So maybe the punchline is that like this thing is like even much closer to ln n than this one was, where we had this expression.